Today we're going to look at Lesson 1-7 on functions. It's on page 47 in your textbook. First, we need to know what a function is. A function has exactly one output for each input. What that means is output is another word for y values or y coordinates. Input would be another word for x values or x coordinates. A shortcut when you're trying to look at whether the relation is a function is to see whether the x values repeat. If the x values or the x coordinates repeat, then you can say that it's not a function. Now let's look at this relation. We have a set of ordered pairs, 2, 1, 3, -2, 3, 1, and 2, -2. We're looking to see whether this is a function or not. So, the first thing I would do is if I have the x-coordinates listed in front of me, I would look to see if any repeat. If none repeat, then it would be a function. If one repeats, one number, then it would not be a function. So if you look at the x-coordinates, you have 2, you have a 3, then you have another 3, and another 2. So both the 2 and the 3 repeats, which means this would not be a function. Because each x value does not have only one output, or each input does not have only one output. Each input has more than one output. Now we'll look at, when you have an equation, how you can tell whether the relation is a function or not. You can see in the first example here, we have 4x equals 8, and there's only one variable, an x. In the second example, you have 4x equals y plus 8. This one has an x and a y. Since if we were to graph these equations, since the x equation, the one with just the x, would be a straight line through the x-axis, we would need to do the vertical line test to determine both of these functions, whether they're a function or not. So, first I would need to solve for x for the first one. And I would be graphing x equals 2. If I were to do a graph, I would go to x equals 2, and I would draw a line, straight vertical line, through x equals 2. So if I were to draw a vertical line through x equals 2 to test whether it's a function or not, if I'm drawing a vertical line through x equals 2, I'm drawing a vertical line through an infinite amount of points on that equation's line. So on this line that I just drew, there is an infinite amount of points. So since there's a vertical line going through an infinite amount of points, we cannot say that this is a function. It's going to not pass the vertical line test, because the vertical line test, it can only go through one point. If it goes through more than one point, then you're saying that the function is not, or I'm sorry, that the equation is not a function. Now for the next equation, 4x equals y plus 8, I would need to put it in slope-intercept form to graph it. So I'd need to take the 8 away from the y side so that the y is by itself, and I get 4x minus 8 equals y. Then to graph this type of equation, we have it in slope-intercept form. So I start at the y-intercept, which is the 8. It's a -8, so I'm going to start at -8 on the y-axis right here. And I'm going to put a point. Then I continue with my slope, which is 4. This tells me to go up 4 to the right 1, because I think of slope as rise over run. So 4 is my rise, 1 is my run. So I go up 4 from the negative 8, 1, 2, 3, 4, and over to the right 1. And I continue, 1, 2, 3, 4, over to the right 1. And if I make a line, I have my diagonal line here. If I were to do a vertical line test to go through each point, and I'm drawing a vertical line, and you can do this imaginary in your head, but I'm drawing it out here for you. So each vertical line there is only going through one point on my equations line. So since it's only going through one point, you can say, yes, this is a function. Now we have something called function notation. Function notation is basically a way of telling you that the equation you are graphing or the equation you are looking at is a function. So you can see the difference between these two equations is that the y in this equation is replaced with the f of x in this equation. And you would say that as f of x. So f of x is one term. It's indicating that this equation is a function by the way that it's written. So that's why it's called function notation. Now in function notation, we still need to realize in this equation that we have in front of us, f of x equals 2x minus 3, that the f of x represents y normally. Okay, so we're going to find each value, and what they're giving you is, if it's in parentheses, they're giving you the value of x to plug into your equation. So, since f of x usually means y, we're not going to plug in the 1 in this first example into the y. We're going to plug it into the x, which is on this side. So we're going to take the 1 and we're going to put it into x, because normally this 1 here is where the x is located. So f of x equals 2 times 1, or 2 minus 3. So f of x is equal to negative 1. Now if I have to do the same thing for the next equation, or I'm sorry, the next problem, we have negative 2. We're going to use the same equation. We're going to take the negative 2 and plug it into x. So we have f of x. Remember, that's not an actual x. It represents y, so we don't plug it in there. We plug it into the x here and solve. So now we have 2 times negative 2 is negative 4. Negative 4 minus 3 would give me negative 7. So my answer is negative 7. Now we'll look at the next number. This is saying find 6 minus f of 5. So we need to find what f of 5 is first by plugging in 5 for x in the equation. So we have 2 times 5 minus 3. And that will give us what f of 5 is. So 2 times 5 is 10. 10 minus 3 is 7. And then if we plug that into f of 5, we're doing 6 minus 7. So our answer is negative 1. And finally, we'll do f of negative 1 plus f of 2. So we're going to have to first find what f of negative 1 is by plugging negative 1 in for x. We get negative 2 minus 3, or negative 5. So that's what f of 1 is. Now we're going to add the negative 5 to what f of 2 is. So that means 2 goes in for x. And we get 4 minus 3, which is 1. So I need to do what negative 5 plus 1 is, and that gives me negative 4, which is my answer. Now these examples are no different than what we were just working with, except for they replaced the x with a t. So instead of plugging in our values for x, we're going to plug it in for t. The same thing would apply here. The f of t in the equation, remember it represents y, okay? So we're not going to plug in our t values into the t here. We're going to plug it into this t here next to the 2. So my equation is 2t cubed. So if I'm finding f of 4, that means the 4 goes in for t. So it's 2 times 4 cubed. 4 cubed would be 4 times 4 times 4, which is 64, and 64 times 2 would be 128. So my answer is 128. Next, we'll look at f of negative 5. If I'm doing f of negative 5, and I'm using 2t cubed as my equation, I'm going to plug in negative 5 for t. So I get negative 5 cubed. Negative 5 cubed would be negative 5 times negative 5 times negative 5, which would actually be negative 125. And then I multiply by 2, so I get negative 250. Is my answer. Next, we're looking at this 3 and then in brackets f of t plus 2. So we need to find what 3 times f of t is and then add 2. So it's asking us to multiply 3 times f of t. That means the entire equation is represented with f of t. So we're going to take 3 and multiply by t by 2t cubed, which is the equation. And then we're going to add 2. So we're actually going to be left over with variables here in our answers, but that's okay. We have 3 times 2t cubed, which gives me 6t cubed plus 2. Since the t cubed is a different term, okay, it is not a like term with the 2 because it doesn't have the same variable or the same exponent. We can't combine this together, so we just leave it as 6t cubed plus 3. Then finally, we're going to do f of negative 3 minus f of 1. So if we plug in negative 3 for t, and then we solve, so negative 3 cubed, negative 3 times negative 3 times negative 3. Negative 3 times negative 3 is 9. 9 times negative 3 is negative 27. So negative 27 times 2 is going to give me my answer. So negative 54. And then negative 54 minus f of 1, we need to find what f of 1 is. So I plug in 1 for t. So 1 cubed is 1 times 1 times 1, which is 1. And 2 times 1 is 2. So our answer is 2. And then we take negative 54 minus 2 to get negative 56. Finally, we're going to look at this word problem. It says a bird feeder will hold up to 3 quarts of seed. The feeder weighs 2.3 pounds when empty and 13.4 pounds when full. This is also located on page 48 in your textbook if you want to follow along. We're going to make a table first that shows the bird feeder with 0, 1, 2, and 3 quarts of seed in it, weighing 2.3, 6, 9.7, and 13.4 pounds respectively. So what that means, we need to make a table of values with our x's and our y's, but we need to figure out which one is our x's and which one is our y's. So, back to when we were doing independent and dependent variables, the x value is always your independent variable and your y value is always your dependent variable. So, the quarts of seed, are they going to affect the weight? Yes. So, the quarts of seed are going to be your independent variables. The weight is going to be your dependent variables because it is affected by the number of quarts. So the weight is going to be the dependent, so that makes it the y. So we're going to put in 2.3, 6, 9.7, and 13.4 on the y side of the table. On the other side we have 0, 1, 2, and 3. And that would be our table. Moving on to determine the domain and range, we talked about that. That is just our list of x and y coordinates. So we have the x's are 0, 1, 2, and 3. So that would be our domain. And our range is the weight, which was 2.3, 6, 9.7, and 13.4. So that would be our range. Now we're going to write the data as a set of ordered pairs and graph it. So if it's a set of ordered pairs, we're going to think about our x coordinates, which were 0, 1, 2, and 3, and our y coordinates, which were 2.3, 6, 9.7, and 13.4. And we're going to put them together as ordered pairs. So 0, 2.3 goes together, 1, 6, 2, 9.7, and 3, 13.4. And that is what we're going to graph on the next graph. So again, we determined that our x values are going to be the quarts of seed, so we can label our graph as quarts for the x-axis, and for the y-axis we're going to label that with our pounds of seed. So we had 0 to 3 quarts, so we're going to label our x-axis, and then we have a range of values from 2.3 all the way to 13.4. So maybe I'll go by 2s to fit it on the graph. Whoops. And then I'm going to plot the points. So 0 went with 2.3, so that's where my first point will be, at about 0, 2.3. Then we have our second point, 1, 6. That's going to be there. And our third point, 2, 9.7, so a little bit under the 10. And then 3, 13.4, so about halfway between the 13 and 14, right there. Now the final part to this question was state whether the function is discrete or continuous, and explain. Well, a discrete function is a function that the points are not connected by a line. So it would be a function that is not an actual equation. It would be a function that has a table of values and an ordered pairs, but doesn't necessarily have to be connected to make an equation. So, in this case, our function is actually discrete. Now, if it's a continuous function is when you draw a line through your function or connect the points. So this would not be a continuous function because we're not actually graphing an equation, we're graphing a set of ordered pairs. So that would be the difference between a discrete and a continuous function, and this would be a discrete function because we graphed a set of ordered pairs. And like I said, if it was continuous, it would mean we would graph an equation and not just a set of ordered pairs. And that concludes our lesson.